All right, so let's get started. Welcome to our keynote session. Today we're going to have Professor Yongdae from KAIST to talk about cellular Metasploit. For those of you who are working on wireless security, you don't need an introduction of Yongdae. But regardless, let me briefly introduce him. Yongdae right now is a professor at electronic engineering department at KAIST. He used to work in US for University of Minnesota for 10 years. Received PhD from Southern California 2002. And his research mostly interested in finding vulnerabilities and security analysis of emerging technologies like drones, UAV, and the cellular network. So Yongdae, the floor is yours.
Thank you. Thank you, Jikin. Yep. Yes, it is my great pleasure to give a keynote here. And my title of my talk is Cellular Metasploit. And I'll get to there more about what I mean by cellular Metasploit. So in the last 12 years, I've been working on cellular security. And these are the kind of list of publications. And most of them, luckily, were at the top conference. And largely, there are two kinds of vulnerability. Two kinds of paper groups. One is the design vulnerabilities in the spec, and the other is implementation vulnerabilities in protocol or memory. But through these papers, many of these papers are finding vulnerabilities, and we report to GSMA, 3GPP, or sometimes Qualcomm, and Ericsson. And during the responsible disclosure, they tell me a lot about this, a lot about their internals. And then we learn more, and then we can write more papers because we understand the internals more. And through that, I understand why there are so many security problems in cellular. And here are 7 secrets you should know why there are cellular security problems. The first is we have a new generation every 10 years. And when we have a new generation, then we have a new designs, implementation, and deployment. That means we have new vulnerabilities in designs and implementations. Okay? We know that scrutiny can improve the security. But every 10 years, we have a fresh code. That's pretty bad. And the cellular network has a network-specific configurations, and actually the operator, unfortunately, the operator is walled garden. They don't like to talk to others about their vulnerabilities. They don't open their testbed for us, right? And sometimes they do make mistakes, but they don't know whether they made mistakes. And patching is really difficult. And when there is a vulnerability in specification, right now, for example, there is a vulnerability in 5G spec. 5G specification is over. And that vulnerability is forever-day vulnerability. As long as we use 5G, we can exploit it forever, right? And also, the patch cycle is really long for even the implementation vulnerabilities. When we report vulnerabilities in baseband, usually it takes 1 year for the finishing of the patches. And security testing is extremely difficult. And in every country, fuzzing operator network, obviously, is illegal, right? And that's why we cannot actually test real devices. And there is no security testing. There is very limited security testing standard. And I don't think we are testing enough. And open source support has been not great. We've been open source some, but it's not sufficient. And when they change the standard, there is a precedence in the sense that government and carriers are the most important people, whether they want to secure or whether they have a new standard in this direction. And probably the customers are the least important people in the whole cellular industry. And they say the government and carriers sometimes it's too expensive, or sometimes governments say we need insecurities. And sometimes, actually, this was actually from the GSMA, told me that, oh, because nobody is exploiting it, we are not patching it. Great. And there's ambiguity in the standard. It's a vague specification lead to misinterpretations and leading to inconsistent security across vendors and carriers. And because it's written in natural language, formal verification, side has been working a lot, but formal verification has been really, really, really difficult. And cellular protocols are multi-layer and stateful. And the documents are spread, all kinds of things are spread in multiple documents, and finding all those nitty-gritty details are really, really difficult. And we don't know, finding someone who knows the whole cellular spec is really, really difficult. And stateful behaviors make the testing really difficult because the spec is so big and also stateful, and when you want to test a particular state, you need to advance each of the device into right state, and that requires actually a lot of research or a lot of engineering. So out of these 7, actually, I work on implementation vulnerabilities and standard vulnerabilities. And these 7 are constituting to, so what I mean by implementation vulnerability is flaws in implementation, such as the protocol or memory. And the reasons for the implementation vulnerability is 1, 2, 4, 6, 7. And reason for specification vulnerability is 1, 3, 5, 6, 7. And because of these, we have so many vulnerabilities. Okay? And there are many threats. Attack models have been proposed, such as fake base station, man-in-the-middle attack, signal oversharing attacks, and sniffing. And there have been so many attacks proposed, and I don't know, 5G has actually significantly advanced. Interestingly, a few months ago, I went to government expo. So this is an invitation-only expo selling some selling devices, such as fake base stations. And these are the some of the advertisements, they say. Mobile identity catching, tracking location. Do you see the drone-mounted image catchers? These are sold, and there's a vehicle-mounted image catchers, and I saw one Chinese vendor was selling image catcher combined with a camera, so that after the image catching, they also take the camera, picture of the person, and then in the back database, they have a, face-based identification. Oh my God. Why do we have this? Because we have the specification vulnerabilities, right? We never secure the 4G, and 5G uses SUSI. That's all we do, right? Interestingly, there's something called private 5G appearing. It's a dedicated cellular network deployed for a specific organization or enterprise. This is from the actually Claude. And when you ask Claude why we use private 5G, it's a dedicated infrastructure, enhanced security, customizable, improved reliability, low latency, higher capacity. And because of these, you can use it for railroad, medical, critical infrastructure, and defense. And I know that US DoD is interested in deploying private 5G for some purposes. But there is actually a fundamental difference between the private 5G and 5G standard, commercial 5G. Commercial 5G, it supports all devices in any situation, and most of the devices are not mission critical. But in case of private 5G, you have to support only specific devices and applications, but many devices are mission critical. I will show you some demo. I mean, it's from the LTE. I don't think the problem is resolved in 5G, but we can, by sending 2 messages, you can actually disconnect the UE for 20 minutes. That's possible. And think about your tank is disconnected for 20 minutes during the warfare. It's not a good news. So considering the private 5G and governments are exploring it, considering all those vulnerabilities, then can we have security enhanced cellular network? What do you mean by security enhanced cellular network? Despite the specification has vulnerability, somehow can we have a security enhanced cellular network? I was thinking about how to do this for a long time. And my conclusion is, let's have Cellular Metasploit. It's an open source, I hope, attacking tools exploiting known or new design and implementation vulnerabilities. Oh, by the way, for those people who don't know what Metasploit is, I get the definition from the ChatGPT. It's a widely used penetration testing framework that helps security professionals test computer systems and networks for vulnerabilities, providing collection of exploits, auxiliary tools for scanning and information gathering, payload, post-exploitation tools. Do we have this in cellular? We don't have this. We don't have this, and somehow we want to secure 5G. How? I don't think we can do it without this. So I will talk about some of my previous research in LTE, and then let's revisit the cellular metasploit later. LTE network is actually very, very complicated. From SIM card, cellular modems, and base stations, gateways, netbox, and billing, IMS server for voice, and there's a 2G connection to 2G, and roaming to other networks. It's extremely complicated structure. What about 5G? What's the change from the LTE to 5G? There's a 5G NSA, not National Security Agency. It's called non-standalone, and 5G standalone. And for the 5G standalone, you need actually 5G core devices and base stations. And for NSA, you can use actually a new radio. That's the only difference. From the security perspective, the only change we have is, I think, is SUSI, which is the encrypted IMSI. Other than that, there is no change.
You can't actually use SUSI with the 4G core network. You need the 5G core network also. So there is no, security-wise, there is no change.
That's right. Yes. Security-wise, there is no change.
Yeah.
So that's why it's okay to revisit the LTE and what can we expect from 5G. So let's look at some of our testing work. So one of the first work, actually, I think there are more than 4, but I kind of summarized 4. So LTE fuzzer was the first fuzzing of the core network and base station. We actually Korean government gave me the testbed access to 3 carriers, and we fuzzed the core network and find 51 vulnerabilities. Out of 51, 36 were new. And this was the dynamic testing of the core network. And door test is a baseband downlink fuzzer to find protocol vulnerabilities. And we found many of them. And base spec and base comp are static analysis to find memory vulnerabilities. And we have 3 more papers in submission where we can, you will see more vulnerabilities in the commercial devices. Okay? Let me talk about some of our testing work. So this is actually not the first work, but I just want to give you some idea. So there was a paper from CCOM saying that there is a fundamental vulnerability in LTE that gives some bad performance. We measured the exact same thing in Korea, and there was no such vulnerability in Korean network. So we were wondering if it is true. So we decided I send my students to wherever the students are going to conference, ask them to collect. Yes, 11 countries, 28 operators, 95 SIM cards. We made 52,000 robocalls and collect 6.4 million signaling messages. Imagine the scale, right? And we didn't do anything great. I mean, the only thing we did was just anomaly detection. Is this network different from others, right? In terms of the detach timing, in terms of the protocol ordering, control flow sequence, or signaling failure messages. Just very simple data analysis. I mean, the data collection was painful, but it was actually very, very simple. And we find this. Interesting thing you need to see is that the US2 was the only operator with a single vulnerability. This was the paper, this was the vulnerability. The CCOM paper claimed that there is a fundamental design vulnerability. That US DoD, a US cellular network, was the only network in the world out of our measurement who has this problem. What do I want to say here? Operators are misconfiguring their network, and nobody is testing it. And it's illegal to test it, right? And I'll give you another example. It's LTE fuzz was a stateless in the sense that we actually fuzz until the key management. So before is a pre-ACA state, we send negative messages or prohibited or illegal messages to the network and the UE and see if those unauthenticated messages are handled correctly. Out of this was, by the way, from the SMP. We found 51 vulnerabilities, and there are UL is actually either base station or core network. DL is the baseband, and there are DOS attack and spoofing. So what do I mean by spoofing? Because for example, we send. So I think property 1-2 was a message without MAC. So it is mandatory to include the MAC, but what if we send message without MAC? Okay? If they accept it, then we can actually spoof the identity inside the message. But there is another very, very interesting case. Suppose I spoof TED ID and send the message without MAC. Then the network drop him. Why? Because network thinks that his device is badly configured. So he should be get out of it. That's why there was so many DOS. But when you know about cryptography, unauthenticated message should not affecting others, but there was so many of them. Yeah. And another interesting thing, so we actually tested Korean carrier 1 and carrier 2, and MME 1 and MME 3 were from the same vendors, from Samsung. From Samsung. But actually their vulnerabilities were different. And one of the root cause was, so the MME, so carrier 2 uses error message, number of error message as their KPI. So they decide to suppress the error message for the authentication failure. who allow me to do identity spoofing. So even from the same vendor, you have a different vulnerability. And Churchun there have done stateful in-depth downlink only negative fuzzer. Negative fuzzer means basically we are generating negative messages, illegal or prohibited messages, and send, and it's a stateful in the sense that we basically change the state. He had about 2,800 test cases, whether those illegal or prohibited messages are handled correctly. This is like a Java exception handling, whether the exception handling is done really well at the baseband. And we found many, many, many vulnerabilities in the baseband. They forgot to handle those, bad cases right. You remember that those vulnerabilities I just mentioned that send without MAC, okay? And because of our LT fuzz paper, now the 3GPP spec release 18 includes a new sentence. Just one sentence is added in the whole specification. It said, if authentication procedure is not successful, the MME shall maintain, if any, the EMM context and EPS security context unchanged. Meaning that illegal messages or prohibited messages should not change the state of the UE. This is the single line. Do we have these vulnerabilities still? Yes. I show you one demo. And this is, I attached the network with a TED ID using emergency registration. And emergency registration does not require authentication. And the phone, you can, let me skip the video a little bit. So meaning that the phone works well, and suddenly the network think TED phone is problematic, and the phone is not responding. How long? 20 minutes. So your phone will be, whatever you do, your phone is not going to be alive for 20 minutes. We have done some memory fuzzing for baseband. And baseband memory fuzzing is interesting. And in this case, actually, we attack in the middle. So while the protocol is ongoing, we inject. So the user is actually downloading data right now. So the UE is in the authenticated state, and the attacker inject memory crash message. And then you have no cellular connection, and your baseband is going to reboot continuously. The baseband crash is interesting in the sense that when you bring fake base station here, and suppose the Qualcomm baseband has that vulnerability, all of your Qualcomm phones will reboot. But what do you think about memory vulnerability in the base station or core network? Probably whole MME, users on the whole MME is going to be down, right? And probably if they reboot, all users will come back to MME. Can you authenticate me? Oh my God, that's gonna be terrible, right? So these are the works we've been doing for LTE. But are there enough work for 5G? We have not started 5G work because the 5G open source UEs and 5G open source core network is not enough. So I think state-aware negative testing for implementation vulnerabilities, as well as the memory fuzzers, are needed. And this is one part of the implementation vulnerabilities. Let's talk about specification vulnerabilities and attacks on the specification vulnerabilities. In the last 12 years, I've been working on actually design vulnerabilities and introduce new attacks. And so there are location identity leaks, and you can actually guess the ID. And this was actually, many of the specification vulnerability was actually discussed in the actual 3GPP. I mean, probably you don't know, but when we write paper, they discuss our paper. They discuss our paper, and sometimes they decide not to patch it because the solution is too expensive. And we don't know actually how many vulnerabilities are remaining. But anyway, so there are accounting bypass, those spoofing leaks, signal overshadowing work, and video fingerprint. I will get to some of these papers. And they are exploring different parts of the specification vulnerabilities. And some of them you can use it for developing applications. And how many of these are patched in 5G? None. I don't think any of these are patched in 5G. So let's get to my first paper. So this was in 2012, where we don't have actually DM or where we don't have anything. The question was, suppose I know TED phone number. So I want to check whether TED is within. Because I decide to pick one, and then I will pick one until the end. Okay. Suppose I know TED phone number. I want to check whether TED is within 1 kilometer or 10 kilometers. That's the question. Then the question was, but then I will call him, okay? Then there will be paging message coming down, and paging message has the target ID called temporary ID, TMSI. TMSI is a temporary identity. Then our question was, does temporary ID change? It should change, but at that time, temporary ID was not changing. Okay? We don't know exactly what TED's temporary ID is, but by calling him multiple times, by intersection the temporary ID, we can find if he's here in the cell or not. Okay? So great. So after finding this vulnerability, we wrote the paper, and they actually responded. 3GPP responded. In LTE, there is a new ID management called GUTI reallocation. So GUTI is actually equal to TMSI. Okay? So there is a GUTI reallocation mechanism, means that GUTI has to change. But you remember the data set? We have the data set from 28 carriers. And we were seeing whether the GUTI changes or not. Out of 28 carriers, 20 of them have at least 1 byte, 2 byte, 3 byte, 4 byte fixed. We can still fingerprint. Great. Surprisingly, there were 4 carriers who were not changing the ID randomly, but after making phone call 10 calls at the same time, they start fixing it. So after this paper, our GUTI reallocation paper, 3PP responded again. They said, yes. From release 18, it says, GUTI has to be unpredictable. So now the spec is finally changed, and probably if there is no implementation vulnerability, probably finding GUTI will be difficult. Okay? But they've been responding. And another interesting attack, it's a very well-known attack, is signal overshadowing attack. Before SIG-over, everybody knew about man-in-the-middle attack. But SIG-over attack is different in the sense that there is a cell tower and the UE. Cell tower sends broadcast messages continuously, right? But these broadcast messages are not authenticated. The easy question is, can attacker at the side inject physical signal at the right time and right frequency? Will that replace commercial base station's message and replace it with attacker signal? My students spent 2 years to implement this, but after 2 years, we were very successful. And I skip the demo, and then I'll play. Oh my God. Okay, let's skip. Okay, so this is a Wireshark. And there are all messages. And the gray area, these are the 5 messages we injected. What kind of messages are injected? There is a message from the base station. Hey, I'm tired, do not attach me. And we inject the message to the phone. The phone says, okay, you tell me not attach. Okay, I'm not going to attach. So you can actually disconnect the UE easily by using signal oversharing attack. And that I'm busy message is not authenticated because it's a MAC layer message. They have no plan to secure the MAC layer. Okay, so you can just detach UE from the network. Great. We developed LTE sniffer, which is many of the messages are not encrypted. So we collect in a cell, we collect downlink messages and uplink messages. But of course, we cannot decrypt some of the encrypted messages. For unencrypted message, we can actually collect a lot of data. And you can actually go to that site. It has currently 1.8K stars from GitHub. Have you seen any of your open source have 1.8K stars? If it is an AI project, probably you can. But I think from the cellular, this is actually a great number. Why? Because there is a commercial product doing exactly the same thing with LTE sniffer from KeySite, which is $25,000. We didn't know it, and we decided to open source it. Oh my God, we lost so much money. Right. So using LTE sniffer, one of the things you can do is you can actually collect DCI message. DCI stands for downlink control information, including what kind of data you are going to resource, or what the data and the resource, the message sizes you will receive, or when you will be scheduled for next uplink transmission. Okay? So DCI releases information about how much data you are going to receive, or when you are going to send uplink message. Using this, one of the paper we have written, I'll get to the localization later, but one of the paper we have written is, can we identify a user in a cell who is watching particular YouTube video, right? YouTube video is actually variable rate encoding, right? But the downlink data usage is actually pretty stable, and if you know the movie, the particular YouTube video, you should be actually identify the ID who is using the video. So you can do actually video fingerprinting by looking at the DCI messages of the particular user. And then I was thinking about, okay, can we do better? Remember that GUTI relocation? We know that someone is within a cell, within 1 kilometer, but Korean police asked me, can we find the phone to the front door of the phone is located? So we were thinking about it. Oh, DCI leaks information about uplink transmission. And at particular time and particular frequency, nobody's sending at that frequency. Suppose we use directional antenna. If the direction is right, I will see the uplink message of the UE. If the direction is not right, I'm not going to see the uplink message of the UE. Here's the demo. I skipped some early part. And this, let me skip a little bit. So there are, hold on. So there are 2 phones. One is at the, here. Oh my God. And there are another phone over the 5th floor. And we have a directional antenna combined with the LTE sniffer. And let's go. The video. So at the center of the field, we run find the phone 1. It's very easy to see the demo, right? If the direction is right, the LTE sniffer is going to see the uplink message. See? And using the antenna technology, we know actually which floor the phone is located. Right? Does it familiar with you? This I got the idea from the actually U.S. military hitting the terrorist leader. So I was wondering how can we physically localize a phone? And it finds the phone on the 5th floor. And this was actually a project from Korean police. There's a phone fraud actually going on, voice phishing going on very, very hard in Korea. And they want to physically localize a phone. And probably 2 months ago, we were able to actually find a phone in a very small part of Seoul. And this red dot is where the phone is located. I mean, it took a while, okay? But, actually, in this case, 3 vulnerabilities are used. So the first vulnerability is that we know the uplink scheduling of the UE, right? The second vulnerability is that what if the victim is not sending uplink traffic? Can we force the victim to send uplink traffic? When you look at the actually scheduling algorithm, it's not that difficult. Because when you have data to send, you tell the base station, hey, I have a data to send. And the base station schedule you. Once base station schedule you, you send the data. The problem is, hey, I have a data to send, is in the MAC layer, so no protection. So I spoof the criminal's identity saying that, hey, I have a data to send. And the base station schedule you. Surprisingly, all the phones we found, once they said the base station telling you to send, they send. Whatever data in their buffer. It's actually very, very interesting. Whatever. They find something in the buffer and then just send it. Another interesting thing, if the phone is actually pretty far from us, then we will not be able to see the phone's signal. Then can I control phone's uplink signal? Strength of the uplink signal. There is an interesting command called TPC, Transmission Power Control. That's in my MAC layer too. So no authentication. Using SIG-over, we tell the phone, hey, your signal is too weak, increase, increase, increase. Then within 1 second, you can actually make the signal strength to maximum. 3 features. Using 3 features, we implement this technology. So before I go to make the conclusion, I've been working with how much time do I have? 10 minutes, okay. So let me quickly summarize. So I've been communicating with the GSMA 3GPP. So, and these are the messages from them, okay? It's unclear how to standardize, enumerate negative testing cases. That's why we don't do security testing standard. And for SIG-over, they say the work is academically interesting, but not for the real world. You know what I said? Can we open source it then? Because it's not real world, right? And they say, we back open source beneficial, safe security research, but no in this case. Why not? If it is only academically useful, they should allow the open source, right? And we asked, why don't you patch the specification vulnerability? Because nobody is exploiting it. Physical localization. Attacks on layer below PDCP do not warrant cryptographic protection. And mitigating the threat may be applicable not before 6G. Okay, there's a forever day vulnerability. You can develop this application to tracking the phone as long as you are using 5G. And 3GPP represented single UE detachment out of scope, though not written in specs. Okay? And on sushi catchers, Christina has written something called sushi catcher. We knew this vulnerability of the sushi catcher, but decided to standardize it that anyway. So they knew about the vulnerability, but in the 5G specification, they decided not to patch it when they design it. So yeah, there are unpatched design vulnerabilities in 5G. We need to develop 5G sniffer, 5G SIG-over, 5G fake base station, MATM, attacks possible against private 5G application domains, security enhanced 5G, blah, 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 blah. And a lot of things we need to develop. And I mean, I've been thinking about IMSI catcher research. Okay, IMSI catcher is really popular. And governments are utilizing it for surveillance, but also governments are worrying about IMSI catching, being IMSI catched when they visit other countries. It's actually very interesting in the sense that they leave the vulnerability in the design so that they can use it, but when they got attacked, they worry about it. Right? It's actually very, very, but interestingly, IMSI catcher, commercial IMSI catcher is not available to academia. And when we write a paper about detecting IMSI catchers, then reviews are always the same. It's unclear if it works against the commercial ones. Of course, we don't have any commercial ones. So my proposal, let's implement IMSI catchers. Let's implement IMSI catchers in academia, and let's open source it and see what cannot be evaded. Okay? And probably the attackers will use it, but anyway, they're going to use it. Why not open sourcing it? Then probably from there, even if we don't have actually commercial ones, I think we should be able to actually detect commercial IMSI catchers by experimenting the design space of the IMSI catchers. So what can we do with the cellular metasploit, including implementation testing and specification vulnerability attacks? We can improve security. For the testing, we can standardize protocol memory testing private 5G, the critical ones, and commercialize our tools with vendors and carriers so that they can improve security. And the long patch cycle, when there's a new vulnerability reported, until it is actually patched, we need some IDS to actually detect those attacks, right? So for the IDS, we need actually these attacking tools, right? And so that the others can learn from us or learn from ours, we should actually develop more tools for attacking the specification, including sniffer, SIG-over, fake base station, MITM. And again, standard vulnerability is good because even if you don't have actually access to the internal of your car or your tank, we can still send the traffic and see how we respond. If you have the cellular metasploit exploiting the specification vulnerability, it will work against any of the implementation as long as the baseband and core network is following the specification, right? And if we have these specification vulnerability exploitation tools, then we know that exactly what should be fixed for the security enhanced 5G. Or maybe if we want 6G, secure 6G, then we can think about how to fixing them in 6G. And of course, we can use them as IDS signatures. And probably, I hope you develop more applications during 5G so that someone can benefit, and also GSMA cannot say that no one is exploiting it. If we develop applications, that's actually applications exploiting this standard vulnerability. Thank you.
Thank you for this talk. This is after my own heart. I mean, this is awesome, right?
I knew it.
Yeah.
I knew you like hands-on.
Yeah, you know, I mean, we should do everything to make this Metasploit happen, right?
Yeah.
The other thing is, I think we should do also something about, I suspect one of the reasons the standards folks don't do anything is they're lazy, right? They don't really, if there's a simple solution, they'll do it. But most often, the solutions are not very simple, right? That it is not a straightforward, simple fix. So I think we should really have research on mitigations as well. And of course, having the data in the Metasploit really would help to come up with some mitigation. So that's my only, wish that we can do that as well as the research community. So what do you think?
Let me give you one example.
Okay.
One example. So broadcast message from the cell tower to UE is not authenticated. Because to do it, you need actually digital signature. For the broadcast message, there's no way other than digital signature to authenticate the broadcast message. Okay? To do the broadcast message, we need a public key. Yeah, for sushi, we have a public key. But what happens in the roaming? Okay? You arrive at the, I arrive at the, LA airport. How do I get the public key of the roaming network? So that means we need root CA, right?
Okay.
And the root CA should be probably GSMA. GSMA refuses to be the root CA.
Right.
And then Apple, they raise their hand. Hey, I can be the root CA. And then everybody says, no, you cannot do it.
Yeah.
So that's the one of the reasons why broadcast message is not authenticated. It's because there's no CA.
Yes.
Like there are those political problems, but also there are some technical problems too. Mm-hmm. So it's not. Right. So there are many problems we knew, and in the textbook there are a lot of solutions, but these solutions are not taken because of the multiple reasons. It's not just the simple is the reason. Yeah.
So you're saying even if there is a technically simple solution, implementing it can be, like CA is certificate authority. On paper, it's not a big problem, but in practice, it's a huge problem. So what your point? Thank you.
And there was another interesting bug. So user plane authentication, full rate user plane authentication is recently standardized. That now every user plane message has to be MAC'd, which was actually pretty recent. And this was actually proposed by Deutsche Telekom. And then, after long time, it is finally standardized. But when you read the specification, it says mandatory of the user plane authentication is mandatory. Implementation is mandatory, but use is optional. And so far, even Deutsche Telekom has not deployed it. What's the point? And just vendors struggle. And just there's a specification, and they say, so specification vulnerability becomes implementation vulnerability because nobody is using it. It's not even implementation vulnerability. It's basically deployment vulnerabilities.
And on that, really, it's really the overhead, right? They don't want to incur. So I think the point you made about private 5G network, the way I'm starting to see private 5G networks is that because they could control it and because they could plan for the overhead, that sure all of these things will become reality, right? So same thing with that data private. The privacy indicator or the
DCI.
Yeah. So that's also the same boat, right? If you want, that's kind of optional. Falls in the optional things also.
In case of DCI, there are multiple reasons, and because DCI can be sent before the authentication, that means you cannot do encryption.
Right.
So, so because before the authentication there is no key, so there are many technical,
Yes.
and we need actually. But one of the things I mean by security enhanced 5G is actually there are unneeded messages. The insecure messages included as additional features, such as access barring. Don't attach me because I'm tired. You don't need actually access barring in most cases.
Okay.
For the private 5G,
Right.
just remove those
Those
cases.
tickets, yeah.
Then you can have actually more secure.
Yeah.
One of the things I learned from actually communicating with the 3GPP folks is that the SA3 is the security working group. Security working group size, RAN people and core network people does not tell the SA3 about their new design. Because when they tell the SA3 always say no. And they are secretly adding new features, which is actually bad for security. So that's what I mean by should we work on ORAN? Or this fundamental vulnerability has not been fixed. You can actually exploit it over the air. What do we do?
Good question.
I have a clarification
Yeah.
question. So you mentioned it's illegal to test those cellular network, but you send your graduate students to different countries. So how do you?
No, we were just collecting it,
Okay.
making phone call. Making phone call. I mean, we actually made a phone call, but automatically using, we never send the traffic in the, commercial network. Yeah.
Hi, thanks for the amazing talk. So I have a question regarding the commercial UE device testing capabilities in 5G. So I think testing commercial devices in a lab environment is a very crucial step to demonstrate an attack in a separated environment. So I think the community has been experiencing some issues when they move testing from LTE devices to 5G, because we have almost every open source radios working properly with most of the LTE devices on the market today. But that's not the case for 5G. That's the case. Everything just stop to work.
So there are two stories behind it. So basically his question is, it's very difficult to attach commercial UE to open source big station, or open source cellular network, or commercial cellular network with open source UE. One thing I've heard, okay, this is rumor, or some inside Qualcomm guy told me. So some of the baseband vendors are developing method to kind of check whether they are connecting with a fake base station or real network. So that could be one of the reasons, if such technology exists. And so I think baseband vendors, they don't like being tested. So that's actually one of the major reasons. And that's actually bad news, because then we are not going to find, not finding vulnerability is beneficial for them. They always, thank me. Oh, Yongdae, thanking me. Thank you for finding so many vulnerabilities. But then they spend like a whole year to patch the whole. Because think about, suppose you find one memory bug in Qualcomm baseband, then how all the Qualcomm baseband has exactly same vulnerabilities? Then how many phones are using the Qualcomm baseband? And you have to test with the baseband level, and then test each of the phones using the baseband, whether the patch works. It's a big headache for them. But they're not testing enough, right? I think we try to help them, but they're not, I don't think they like us. Yeah,
Yeah.
it's difficult. Yeah.
Thanks for the very
Yeah.
valuable insights. Just one thing to add here. So I recently noticed like iOS, I think they are opening up the capabilities with private 5G. If you go to the most recent release of iOS 16 or something, they have a page that explicitly talk about how to make an iPhone to be compatible and tested with a private 5G environment. But that's not true for Android. And Android, I think, for Qualcomm and other basebands, there's still a huge problem in those capabilities. But iOS, I think they're trying to make progress on that. So that's a good thing.
Yeah.
Yeah,
I mean,
I can add that actually the Android phones, it was hard for us. We actually connected commercial phones to our own systems, both commercial base stations and non-commercial base stations. And what we found out, some of the phones, although they say it's completely configurable, it's not programmed for any operator, they actually retain code inside that identifies with a particular network, right? Like Verizon or AT&T. So there is hard coding that, I mean, there are ways to go around that, but it takes a lot of work. So there are some things built inside the commercial UEs that makes it hard to connect it to anything that's not commercial network. But those are all implementation stuff.
Yeah.
So.
Yeah.
No more questions. Let's thank Yongdae.
All right. Thank you.
Next, we have to still have the paper session. So we have 2 more papers. One will be, one is the Mobi Dojo, will be presented by Yunwoo Lee. Yunwoo is a master student at Ohio State. He's one of my students. So he's going to talk about Mobi Dojo, a virtual security combat platform for 5G cellular network.
Hello everyone, my name is Hyunwoo Lee, and I'm excited to present Mobi Dojo, a virtual security combat platform for 5G cellular networks. This work is a collaboration between the Ohio State University and SRI. 5G enables a high-speed data transmission, ultra-low latency, and a massive connectivity. But deploying and securing 5G network is highly complex. For those new to 5G architecture, it might seem overwhelming. It consists of many components, but we can simplify it into 4 fundamental elements. First, UE. These are devices such as smartphones and IoT devices that connect to the network. Base station handles a wireless communication between UE and the core network. Core network is responsible for authentication, data routing, and network management. Data network is a real connection to the internet. With these 4 fundamental elements, we can gain a clearer understanding of 5G network. And here's one new feature in 5G, network function virtualization, where those components can be deployed on cloud-based infrastructure. While 5G brings advancement, it also introduces security challenges. Here's one of the root causes of inherent vulnerability. For the control plane traffic, encryption is optional and integrity checking is mandatory. And for the user plane traffic, both are optional. This is one specific real-world example. Over 100 exploitable security flaws have been discovered in major open-source LTE and 5G network implementation in 2024. Despite the availability of open-source 5G platforms, they present several challenges. First, they have a complex installation process, and mostly they use command line-based interface. And lastly, they do not offer security testing features. To illustrate the challenges, let's look at two existing 5G platforms. First, open air interface. It is widely used open source 5G software, but it requires a complex installation and configuration. Next, Colosseum. It is a hardware-based platform for scalability. However, it does not offer any GUI software for 5G deployment and security testing features. To address these challenges, Mobidojo enables an easy deployment of web-based GUI and enhances security research with attack simulation plugins. Let's watch a short video demonstration of Mobidojo.
5G network architecture, a control panel, a log monitor, attack simulation plugins, and a shell terminal. Let's go over them one by one. On the left, there are buttons to check the network status and connectivity. The control panel on the right allows you to control your 5G network. First, let's turn on the 5G core network, and you can check its status using this button. The core network functions are visualized, and the red color indicates the function is not ready yet. After a few seconds, the boxes turn green, and the core network functions are successfully deployed. Next, we start the base station, or G-Node B, and we wait until the base station is initialized. And finally, we start the UE containers, which connects to the base station through simulation. These 5G network components, including the core network, base station, and UE, are deployed based on the open-sourced Open Air Interface project in a virtual Docker environment. Once all the components are deployed, we can use this button to verify connectivity. A pop-up message confirms that the UE has successfully connected to the data network. Behind the scenes, this process involves running a ping test to google.com from the UE. The off buttons in the control panel allows you to turn off each component individually or simultaneously. Next, you can capture traffic for the core network. By clicking the traffic capture button, the system uses T# to capture actual traffic from the core network functions, saving it as a PCAP file that you can analyze it offline. For example, you can use the Wireshark traffic dissector to analyze the 5G traffic packets. Additionally, you can save logs and PCAP traffic for the UEs and base stations. These files will be stored locally in specific directories for further analysis. The log monitor provides an overview of all error and warning logs. By clicking the Monitor Log button, the log entries will be displayed. You can also see the number of error and warning logs. The drop-down menu on the left allows you to filter these log entries for specific 5G network component, such as a specific network function or UE. The Attack Simulation plugin enables users to simulate real-world 5G attacks within a controlled environment. The initial release of Mobidojo has integrated 7 attack scenarios from our prior work 5G Spectre. You can use the UI widgets to select the attack and set the attack parameters. The first attack example is BTS resource depletion. It requires 2 attack parameters. Attack level is a value that defines the intensity of the attack. Delay is the time interval between each attack session. These inputs allow users to fine-tune the attack's impact, making it suitable for various testing scenarios. After setting the parameters, we launch the attack from the panel. This attack is conducted to overload the base station by creating massive fabricated UE sessions to consume excessive resources. This essentially causes service disruption of the base station and disconnects all the connected UE, triggering a denial of service attack. After the attack, we use the Check Status button and can see that the base station and UEs are disconnected. We also enable users to build and launch customized attacks in the 5G test network. In this panel, user can select a local customized PCAP file and inject it through the NGAP interface between the base station and the AMF core network function. This is done through the integration of an open source tool called 5G Replay. To build customized payloads, MobiDojo offers a PCAP modifier for manually or automatically creating 5G PCAP traffic files. In manual mode, we first select a local PCAP file to edit. The interface visually separates from Ethernet frames to IP, SCTP, and NGAP frames using different colors. The SCTP and NGAP protocols are integral to the 5G signaling plane for managing connections, mobility, handovers, and session management between the 5G base station and core network services, such as AMF. You may click on a specific hex value at an offset to display its value and modify it to a new one. Similarly, you may modify payload values at arbitrary offset. By doing so, a customized and new PCAP file will be generated and saved locally. Being able to capture, modify, and replay SCTP and NGAP packets enables users to generate 5G PCAP traffic datasets for a wide range of real-world attack scenarios. These datasets allow users to design attack test suites that can accelerate the development of new detection and mitigation services within 5G networks. Upon reviewing the modified file in the Wireshark dissector, you may notice that this packet is labeled as malformed packet due to previous random edits, but the actual changes will reflect the desired modifications accurately. So when manually editing traffic, it's essential to follow the precise packet structure from 3GPP to ensure valid modifications. The PCAP modifier also provides an automatic mode that helps generate seed packets based on the 5G SCTP and NGAP protocols by randomly inserting values into protocol fields. This mode starts from an NGAP message type, such as an initial UE message. The modification options are based on the NGAP message structures from the 3GPP specifications. For example, selecting 3 as the modification part and specifying 256 as the number will generate 256 packets. You can choose between random or in-order edits. The modified packets are saved into a new PCAP file. Upon review the generated payloads in Wireshark, packets beyond certain thresholds might appear as malformed packets due to undefined values, but valid packets will be correctly generated as specified. This automatic payload generation is still a beta feature and will be further improved in our future development. Finally, the integrated shell terminal offers users with fine-grained control capabilities with the system. It includes both a small view and a synchronized large view for easier usability.
Yes, that's it. MobiDojo supports multiple real-world applications. First, it provides hands-on CTF competitions. In education, it can help students easily understand 5G security concepts. It also allows researchers to analyze and test their 5G security research. And lastly, it can help to test and validate real-world attack scenarios. With these 4 applications, MobiDojo provides 3 key benefits. First, it facilitates an easy understanding of 5G network, enhances accessibility for all users, and saves time and effort through automation. To summarize, MobiDojo offers user-friendly 5G network deployment, real-time network monitoring, and security attack simulation and verification. with these features, we believe that Movidojo will play a vital role in advancing 5G security research, education, and real-world defense strategies. Thank you for your time and attention. If you want to know more about our 5G security research, please visit our SURAN website at 5gsec.com. And we also published our source code and demo video, so feel free to visit below QR code. Thank you.
Thank you for your talk, children from Kyung University. So do you have any other future plan for extension? For example, fuzzing. I can see that you can also have fuzzing from the binary level, or I don't know, some other attacks.
Yes, we have several future goals, such as we aim to extend our deployment to the with the commercial UE and commercial core network, and deployment on the cloud-based service like AWS. And also, you mentioned the fuzzing phase, and I showed traffic modification with 3GPP specification. So it's gonna be our future work to make a fuzzing traffic using 3GPP specification.
Okay, so maybe against the UEs or within the core network or other network functions, or.
Oh, sorry about.
Any specific target that you're looking on?
My target is core network.
Okay. Oh, okay. Thank you.
Okay, so yeah, interesting work. So I think one purpose, this tool, you mentioned this tool can be used for education purpose. So for education purpose, we have so many, for example, for C-Lab, so we can do so many different attacks, even we have so many materials, anybody can use that virtual machine, can download, can configure, do system. So I'm thinking about, it's possible we can also utilize this tool to design many labs, and even can be used for lateral security courses. So, but I can see it still is very preliminary. But I think even it's very useful if you can host, even you mentioned about the AWS, student can do this lab online, even remotely. So this should be very interesting. Yeah, very much.
Yeah, thank you for your feedback.
Yes. No more questions. Let's move to the next presentation. Thanks.
Thank you.
I think you collect, or you did it right. Maybe just collect it. Yeah.
The audio in your presentation?
No.
Okay, perfect.
I have a thing, so it should work, hopefully. Or not. I don't have HDMI. Oh, okay. All right. It's okay, I got it. Yep.
So next paper will be presented by Tolga.
Right.
Okay, Tolga. So he's going to talk about towards establishing our systematic security framework for next generation cellular networks.
Right. Thank you. And so I'm from a small cybersecurity company in Northern Virginia called A2 Labs. I was in Virginia Tech before that, and we actually collaborated with Professor Licia Zhang from UCLA for this work. And so the agenda for this presentation, first I'll motivate the problem, right? And I'll talk about named data networking, which is kind of the foundation of how we try to solve this problem. Then I'll present our new core design that we're trying to sort of sell here, a proof of concept, some evaluations, and then a lot of the future work we have planned. So the motivation. And so I think everybody is familiar, but the primary difference, especially in the core network from the predecessor LTE, is that we are now transitioning into an era where instead of having physical network functions attached to proprietary hardware, we're going to start having these virtual network functions in a cloud and softwareized environment, thus enabling a much more flexible service delivery, right? And if you look at this more familiar picture, the service-based architecture, right? The key things I want to note here before I motivate the problem is these are virtual network functions that communicate over REST APIs using HTTP, right? And the NRF facilitates some discovery operations and so on. But while the internal 5G procedures seem to be well studied, one thing that is not so well studied is the network security model, because it's kind of like set in stone, right? These are application layer entities that by default have to use existing network security protocols, right? TLS, IPsec, and so on. And 3GPP has in fact dictated this in some of their standardization files. So if you look at this figure, how does it work, right? If I'm a VNF, and I want to communicate with another VNF, I will have a certificate authority like a web PKI. Maybe for now they're private operator-based PKIs. Configure a certificate into me, then I will have to establish a point-to-point security secure session with my co-VNF, and then basically do all my necessary 5G procedures, right? This is a very host-centric approach, granted robust way of doing network security, right? And it's worked so far. But what's happening is, and this is a very real transition, we are now looking at actually deploying, and it's been talked, right, before this presentation, that we're looking at deploying our core network in a public cloud environment. Right now, if you even go to AWS, they're partnering with Fujitsu. You can look it up, the AWS Telco Network Builder. You right now can actually, if you have your core components, you can deploy them in the cloud. Azure Private 5G Core, right? You can sort of get an agreement with them. They will deploy a private 5G core for you, for your enterprise needs, right? Granted, they're becoming deprecated, I believe, in September, but I think they have other partners with Ericsson and Nokia and so on. But the point I'm trying to make is this cloud-native adoption of the 5G core is a very real thing. And it's coming, right? So to that end, how do we adapt our network security model where we're going to have this potentially extremely distributed 5G deployment in a previously unexplored, like unprecedented scale to be deployed in a cloud environment? And with that, I want to talk about NDN, right? So name data networking, right? Which is a future internet architecture model that Professor Zhang kind of pioneered about a couple of years ago. But the idea with NDN is that everything in your cyberspace now is a piece of data. So what did I say, right? Host-centric communication. It used to be the case that I would have to know your IP, I would then have to establish a secure session with you, then we would communicate over that session, right? I mean, if robust, but not very efficient when you consider the scale of things and where they're headed, right? When everything is a piece of data in your cyberspace, the data itself, the users, the keys and certificates, right? At that point, this no longer becomes host-centric, it becomes a data-centric, right? So how does communication work in this ecosystem, right? I, as a service consumer, will start by sending out an interest packet, which would basically be comprised of a semantic name that designates the piece of data I want in that cyberspace, right? So in the context of 5G, which I'll show in a minute, this can be basically a piece of data that a VNF produces for me. At this point, I do not need to know your IP. I do not need to know who you are. I just send my interest out into the network. And the NDN knows routers will take that interest, it will forward it to where it is held, and then I will receive my data basically in a packet which has security embedded into it, right? A signature embedded into it, which if you want to authenticate it, you can basically fetch the certificate in the exact same way using the interest method, right? So this is NDN, right? So this forms the foundation of the shift we're proposing in this paper for the, well, initially for the core network and then eventually maybe at a larger scale, right? So what is this model that we're proposing, right? So to first understand how this synergy works, you can kind of see in this graph at the x-axis, the key features of the NDN networking model, right? Data-centric security, semantic entities, and seamless data access. And on the y-axis, how they synergize with the current architectural components of 5G, especially the 5G core, right? So you have the architecture, which is a multi-domain, multi-tenant, multi-slice deployment. Then you have the communication model, which uses the Common API framework. It uses, maybe not necessarily to a non-expert, but to experts who understand, they're essentially semantic APIs. Like if you look at the APIs of the 5G core components, you can understand the data that's being sent to them simply by the name. And in deployment paradigm, as I said, a hierarchical cloud microservice-based deployment. So with these synergies, we come up with 3 key augmentations, right? We propose an NDN-based trust management for domains and network slices. We propose data-centric VNF communication and seamless data access. First, NDN trust management for next generation. How does this work? So here you're seeing our vision, our interpretation, well, and I would assume many people's interpretation of how the 5G hierarchy looks. You have a domain, let's say, that has multiple tenants within it, and then that tenant manages multiple network slices, within which there are multiple virtual network functions, which have individual microservices, and they produce a data for the outside, right? So we are proposing that we can use NDN semantic naming convention, which is hierarchical, that it captures the relationship between these entities so that you, as an operator, will be able to basically establish transitive trust relationships without relying on a centralized certificate authority, which is really the key here, right? Because with NDN, since it's not host-centric, there's no need for a certificate authority. Like, you do not need someone to pre-configure certificates for you so that you can actually establish a secure session. And with that blockade gone, you can establish this transitive trust relationships using this naming convention, right? And this kind of really maps very efficiently into this multi-tenant and multi-slice communication environment, right? Because with this naming convention, you can kind of design these trust schematics within NDN that will help you define this transitive trust relationship. And second, so I already showed this, data-centric security, which will be the augmentation, but first I'm showing this again. So this is how it works right now, right? Host-centric, traditional 5G core network security, certificate authority configures certificates, then secure sessions are established, after which whatever 5G core procedure you want to take place will take place. But, so one, in an environment where VNFs have the potential to be very ephemeral, right, migrated, crash for whatever reason, this can have somewhat of an operational overhead, and it can affect your ability to maintain security efficiently, right? So with NDN, you eliminate this point-to-point overhead, because for one, since no longer I don't need to know your IP, that means I don't need to discover you. Like, that not only eliminates the point-to-point session setup overhead, but also eliminates my need to discover anything, right? Basically, the functionalities of the NRF, to a certain degree, are becoming obsolete, right? The ability to discover or facilitate discovery. This is no longer required here. And secondly, the trust itself is, again, since we don't have certificate authorities, they are kind of intrinsic to NDN's, NDN's trust schematics, which will become more apparent in this seamless data access augmentation, where, say you have a VNF, as I said, that you want to migrate, right? How would this work in the traditional model? You have deployed in one cloud server, you just migrate to another one. When this happens, you have to maintain your connection state. This is not easy to do, right? I mean, or you have to reestablish it, right? So let's just say you're reestablishing it, because I think that's what people do. I'm not. When you do that, again, it's well known, it's safe, it's been done for a very long time, but it can have downtime, especially for low latency, time-sensitive applications. This can be a problem. So with the NDN-based model, since you have already defined your trust relationships using the NDN trust schematics, which are kind of like underlaying your entire network, you don't need to do that. Like, when you integrate a VNF, all it needs to do to integrate itself into the ecosystem is basically just send interest packets and receive data. Now, obviously, saying all this is fine, but we have to build this to show it, right? So, and the way we build it is we try to conform to cloud-native design as much as possible. To that end, we use the concept of the service mesh and the sidecar proxy, which are for Kubernetes familiar people, a sidecar proxy would be a container inside the pod of your application of interest that will abstract away any networking functionality. So ideally, if we want to build this, we would replace every single IP-capable node with an NDN router, but that's not going to happen, right? So we have to build an overlay, and this is how we do it. So we have, again, sort of a hierarchically shown deployment, right? So you have your pod, which is a 5G core VNF, and then you have the NDN sidecar proxy next to it, which provides common API translations to interest packets, right? So, and then at the cluster level, at the node level, we have individual NDN routers deployed. And then finally, at the cluster level, we have basically a bunch of NDN routers. But again, the key thing is that red domain you're seeing, that's the NDN domain. From the perspective of the 5G core VNF, which is in that gray area of the pod, it's seamless. Nothing is changing. It's not even aware of it's being used over the NDN domain. And some preliminary evaluations for this. Now, these were not in the paper. I do want to show them anyway, because I think it's interesting. We are able to see some improvements because it's expected, right? You get rid of some of these, we get to essentially reduce key service chain overheads, like 5G authentication, key agreement service chain, session setup, and so on. And the reason for that is very simple. There's no more discovery or tokenization required. And just to be clear, I don't think there's open source implementations that show tokenization, so we have to also build that from scratch to actually compare with this. So we actually built Auth2 into 5G core and then compared it with our version to, well, get these results. And the final piece of result is everybody wants to know about cost, right? How much is this going to cost? And how do you know this? How much computational power does it consume, right? And approximately for, let's say, for a sidecar, NDN sidecar proxy processing 2,000 requests per minute, it will cost you about $0.01 US on AWS per VNF to implement this, right? It's not substantial, if you ask me. I mean, it's not negligible, but not substantial. Some future work. Now, again, we want to do some more comprehensive measurements, actually conduct some specific attacks and see how the traditional networking model compares with the NDN. And then more importantly, I believe this carries implications, even though our initial investigation was into the cellular networks, it actually carries implications for the cloud native community, because if we are able to build a container network interface that does provisioning of the Kubernetes admin plane through NDN, that is something will be of interest to something beyond the cellular community, right? And just last but not least, I did see this is an unofficial slide I added at the very end. I have seen a lot of talk about non-terrestrial networks, about how they synergize. And I believe with this, it's also possible to facilitate a seamless connectivity layer that can serve a bunch of different customer segments and their needs when they have different access options, right? When they have, let's say, non-terrestrial networks, Wi-Fi, 5G, and so on. I think I'm a little bit above my time limit, so I'll just end here, and thank you, right?